So what I wanted to do is something that I've occasionally forgotten to do, which is teach students the basics of how to work with data. So thinking back to last lecture, we talked about data structures, file types, etc., fields, attribute values, things of that nature. So what I did right before class is I actually just accessed the data, starting with when I first started doing this activity back in 2019, all the way through to right now. Looks like someone just got one in at 8:24 a.m. And what I did is I downloaded this. This is Google Sheets. I just said, hey, let's download this as a comma separated value. And then I put it in the Teams channel under lecture content. So what I'd like you to do is go ahead and download that. And I'm going to show you how to turn this into your own layer in ArcGIS Online. So when I downloaded the file, it appeared in my downloads folder. Just going to go ahead and open that up in Microsoft Excel to show you what it looks like. So we have a timestamp field. This is really nice because we can apply time filters. We can actually use time sliders to view certain ranges in the data. You know, it might be interesting. I've been doing this long enough to see if there's a change in the precision between 2019 and today, right? That's like at least 4 generations of iPhone, I think. So let's actually close this in Microsoft Excel. And I want to show you what this looks like in a text editor. So it's a comma separated value. So to open this up in a text editor, you would just right click on the file. It's going to depend a little bit on your operating system, and you can do this in a Mac as well. Just say open with and choose either Notepad or WordPad, just some text editor. So we talked about delimiting last time, right? These data, the fields and the attribute values are all separated by commas. And then individual rows are separated by the enter key, right? They're on a new line. Note that there is not a comma after the last row. Any questions so far? People managing to find this file and open it up on their own machines? Cool. If you're not in the Teams channel, you can request to join using the link on D2L. Hopefully I have any requests right now. I'll just make sure. Oh, a couple people. All right, so Microsoft Excel knows how to deal with a .csv file. Over here, we can see the file type when you're actually hovering over the file in your operating system. You might actually see the file name with a .csv after it. Let's say I instead change this to a .txt file. See if it'll do that. No, it won't do that with this operating system. Well, let's not deal with that today. So this is a CSV. Excel knows how to deal with it. ArcGIS Online also knows how to deal with it. So the next thing I'd like you to do is actually go to arcgis.com and log in with your username and password. That's CMSU, of course. Again, raise your hand if you're following along so far. Cool. All right, so this is kind of one of the magic step, right? How do we convert a .csv on your file system on your computer to a hosted feature layer that lives on a server in ArcGIS Online. To do this, you're going to want to go to the Content tab. I want to also mention there is a similar workflow for doing this in ArcGIS Pro, which you'll learn in lab, but I'm just focusing on online for this lecture portion. And right here where you see that button that says New Item, go ahead and click that. It's going to show you kind of a list of different options. You don't actually have to choose one of these if you're uploading a file, because it'll read the file and actually figure out what the options are for you. These options down here are to allow you to create blank layers. Right? You could start with creating a layer that's a blank point layer, and you can use the editing tools in ArcGIS Online to create features in that layer just by clicking on the screen. But you do have to create a feature layer before you can actually edit it. For our purposes here, you can either click on this area to upload your file, or what you can do is just drag it in. So I'm just going to open my downloads folder, find that CSV, just drag it into that area. And it's giving me a couple of options here. How would I like to add the file? Add the file and create a hosted feature layer or table. Or just add the CSV to store in your workspace to do other things with. There are reasons you might want to do both of these, but for today's purposes, we're going to create a hosted feature layer. Hosted meaning it lives on a server, people can access it and work on it at the same time. So now it's reading the file, and what it does is it automatically detects the fields. The fields have to be in that first row. That's where ArcGIS Online is looking. It's also going to figure out what the data type is. If you've ever taken a computer science course or done any coding, you probably recognize these terms. But these are important because you do have to maintain compatibility between fields, and you might want to choose different data types depending on what type of data is being stored. For example, like a zip code is a five-digit number technically, but you don't actually want to treat that as a number in some cases. You'd rather store that as text, so that you can add a 0 in front of it, right? You're not necessarily multiplying or subtracting zip codes from each other. So that's a case where ArcGIS Online might say, oh, this is a bunch of numbers in this field. I'm going to try to make it a number data type, but you might actually want to choose a text data type for that instance. So we can go through these, and timestamp is recognized as a date. That is great. That's what we want. Latitude and longitude are double, meaning that these are numbers that have decimal places with a lot of precision. That's good. That makes sense with our lat long coordinates being relatively precise. A string is a text field. So the text responses to these two questions, what device and software did you use, and what is your name, those are going to come through as strings. And that's the only possible option because it's the only compatible field type. You can also select your time zone. The default assumption for times on the internet for working with data in general is universal coordinated time, UTC. But, and I think actually the Google form would have captured universal coordinated time. But if you were punching in times manually in Mountain Time, you could also select that from this dropdown. You can also select which fields to bring in, right? If there's fields you don't actually need, you can get rid of those. Questions? Right. So once this is all set, you can hit next. It's going to ask you how to actually create your spatial features. The default here is latitude and longitude, and it automatically detected that you have a latitude and a longitude field. If you name it something like lat long, it'll also detect, or XY, it'll probably figure that out as well. But if you have another field name in your Excel document, your CSV, it might not automatically detect, and you might have to choose these from the drop-down menu. So this is just, right, this is assuming that you're using latitude, longitude coordinates in a specified coordinate system. going to use that information to plot your points on a map. There is another option here where it can use addresses or place names. This, who can tell me what that is called, right? If you're locating features based on a address or a nominal location like a place name. Anyone remember that term from last week? Anyone? Geocoding, is that what you're going to say? Great. Yeah, geocoding. That's when you use an address or a place name to get the coordinates plotted on a map. Reverse geocoding is if you had XY coordinates and you wanted to get the address, right? You might have a bunch of XY coordinates and maybe you want to send out a mailing list, so you want to get those addresses. And you can do that with reverse geocoding processes. So we're going to select latitude, longitude, hit next. I already did this once. So if the name is already taken, so I'm going to rename it. You can choose which folder in ArcGIS Online to store this in. You can assign categories if you would like. This is useful for if you're sharing this publicly and you want people to be able to find it. Tags, this is also a useful organizational tool. Oftentimes I put G284 if this is teaching material for G284. And I can add a summary if I would like, and hit save. So if you followed along with all that, you just created your own hosted feature layer, right? So thinking about your map project, creating your own maps, if you can make a table with the attribute values, with XY coordinates, etc., you can upload that data and work with it in ArcGIS Online. Let's go ahead and open it in Map Viewer. See a couple of our erroneous responses here. I'm not going to click on those because I don't want to call those people out, but probably relating to just typing in the numbers wrong or switching latitude and longitude. Not sure what went on over here. Probably a rounding issue, like actually only 2 decimal places were put in. But most people managed to find a reasonably good location. Notice there is some scatter. I'm going to change up the base map by going to the base maps tab over here to get something that doesn't drown out the data. So I'm just going to choose light gray canvas so I can see my points better. Actually, what I will do is choose satellite imagery because I want to be able to see that maintenance hole cover. So that is sort of the spread in our data. And for the rest of the lecture today, I am going to tell you about why we get this kind of drift in our GPS locations. What are the sources of error in taking GPS measurements? But overall, we're doing pretty good. Let's see who has the absolute best measurement possible. Gold star today. Last semester, someone named Cody Matz. But yeah, some of these points are plotting right on top of the true location. Nice job, Shay. We could also symbolize this into various different ways, right? We can select our layer, open up that symbology tab or that styles tab. You might want to do a heat map visualization. I'm going to stick with location though, because I want to take a measurement. Go on here to options, and let's change this to a much more visible symbol. Basic shapes. And then let's choose our color to be like a nice bright blue. Under map tools on the right side, what we can do is measure distances on the map. So I'm going to start from right in the middle of that maintenance hole. Let's go out to where like most of the data are contained within an area. We might say like 90% of the data are within this radius here, assuming you actually typed it in correctly. corresponds to about 20 feet. So you could be 20 feet west or 20 feet east of the true location with a kind of consumer grade GPS device on your phone. Do that in meters. Now it's about 6 or 7 meters. Seems about right. Questions? Cool. So I'm going to give you a little extra credit for this activity. If you haven't done it yet, you can do it today and get your responses in. And feel free to save this map in ArcGIS online if you would like. Well, I kind of rushed through this last time, but just a reminder, if you want to access your attribute data from Map Viewer, you can hit that button to show table, hit the drop down on the layers pane, show the table. You can actually explore the data. You can sort the data, etc. What we can also do see if I can remember how to do this real quick, but I want to take advantage, excuse me. I want to take advantage of the fact that we do have a time field. Under our layer settings, there should be an option to enable time. Well, I'll have to show you that next time because I can't remember exactly how to do it. But yeah, we can use that time field for lots of cool things. Let me just show you an example of using an attribute value to symbolize. If we go over to styles on the right side, and if we have our GPS precision activity layer labeled, we can specify a field that we'll use for symbology. So up here where it says the plus symbol plus field, we can use a number of different fields to symbolize our data. We can't use the fields that are being used for the XY coordinates, but we can use any other fields. So we could use the device and software. And then once we choose a field, it gives us some different symbolization options, right? It allows us to specify a different color for different text responses. These data are a little messy because I had people just kind of type this in manually. But if you want to limit this to a set of maybe 5 options, you could specify that in your form, have it be a drop-down menu, and then people could choose between like iPhone, Android phone, Garmin handheld GPS, GPS watch, whatever. And then you would have these choices. You could change how each one is symbolized using the style options. Pretty similar to the symbology pane in ArcGIS Pro. One final thing, you can use your fields in the pop-ups. By default, it kind of just takes every field and makes a table out of it. But what you can also do is you can click that Add Content button, and you can choose a text option. You could write, I kind of showed you this briefly earlier. You could say, this coordinate was collected by, and then hit the curly brackets, choose name, on, and then you could choose timestamp. Say with, and then choose which device and software. So this coordinate is collected by Eddie Webb on September 6, 2022 with iPhone 12 Gaia app. A little bit easier to read than that table of coordinates there. Might be a little bit more professional, right? Anyone know Eddie? All right, so we are looking at GPS data. We've got sort of a sense of what sort of reliability we can actually expect just from our hardware. And then there's also other sources of error, like human error, of course. Putting coordinates way over here, etc. And we're going to talk a little bit more today about what are the major sources of error in collecting data with GPS. This is a form of primary data capture. Okay, so in lab this week, I put a message up on Teams. Teams is not great with notifications. I realize this because I miss things all the time. But check Teams before lab, and I put up an announcement that I want you to bring a device to lab if possible. By device, I mean any sort of smartphone, any Android or Apple smartphone will be able to run this software for free. You can bring a tablet as well if you prefer a larger screen. If you don't have one of those options, talk to your TA. We have a couple of loaner devices we can loan out, or you can team up with someone in your class. But there is an app called Field Maps, and it's published by Esri. And if you have that downloaded and installed on your machine, before you get to lab this week, that'll save you some time. Its login interface is just like ArcGIS Online. It's going to ask you for your single sign-on through Montana State to our Spatial Sciences Center at MSU organizational account. What you're going to be doing is collecting point line and polyline data in the field with this app. You will capture some geolocated photographs that are actually attached to your locations. So simulating if you're someone working on a GIS project and you're the field worker, right? You're actually in the field collecting primary data. You will then return to the lab and create a simple web map in ArcGIS Online, and you'll assess the positional accuracy, much like we did earlier with your GPS survey response. All right, so what is GPS? How does it work? We have courses in GPS at Montana State. If you're doing a GIS related degree, there's a few options, but there is a GIS and planning degree in the Department of Earth Sciences. You will take GPS courses. So what is GPS? GPS stands for Global Positioning System. Actually not sure if this number has changed because it's a couple of years old, but a couple of years ago, there were 24 satellites orbiting the Earth providing this service. And it was operated and maintained by the US Department of Defense. There are other GPS satellites that are operated and maintained by other agencies as well. This all started with the US DoD. And so satellites are basically rotating around the Earth in a constellation, and they are emitting a radio signal, which is picked up by any GPS-enabled device. So, I mean, that's kind of nuts to think about, right? You're holding a little computer in your pocket that has an antenna that can pick up radio waves from space. Pretty awesome. And there's just a really simple formula that is used to calculate position. Distance equals rate times time. So the rate of those radio waves and how long it takes to travel from the satellites to your device tells you the distance you are from the satellites. And then by triangulating, or actually ideally more than triangulating, talking to multiple satellites at once, you can precisely locate your position on Earth. So this concept really originates in the 1970s, and it was for the military, right? It's pretty obvious why you would want GPS. You want to have really good positioning data for navigation, targeting purposes, etc. GPS consists of three major components. In space, we have the satellites. On the ground, we have the user and whatever devices are being used to receive signals from the satellites. And then we have control, which is actually maintaining that cluster and actually figuring out when interference occurs and how do we actually correct for that interference. Control segment is operated by the US DoD, and now the Department of Transportation shares management. That would fall under the authority of Mayor Pete. So currently, of course, this is open to everyone, everywhere on Earth. At first, this was just a Defense Department technology, and they actually maintained control over it so they could turn off precision for civilian users anytime they wanted to. It doesn't happen anymore, though. Satellites themselves are actually powered by solar panels. They point at the sun, they get their power from the sun. And each of these satellites has at least 4 atomic clocks. So these are clocks that are based on the frequency of vibrations of atoms. They are the most accurate clocks possible. So for example, a quartz clock, which is based on SiO2 chemical structure vibrations, they're accurate to approximately 1 second per month. Sorry, the quartz clock is like what I have on my wrist here, a cheap fossil watch. An atomic clock, on the other hand, is accurate to roughly 1 second per 20 million years. So if you ran this clock without any corrections for 20 million years, it would be off by 1 second. So the national standards for running one of these atomic clocks is that they have to have an accuracy of 10 to the negative 9 seconds per day. So 1 part in 10 to the 14. The satellites are in 6 orbital planes. They orbit the Earth at, I'm not going to ask you how many orbital planes on an exam. Just trying to give you a sense for how this works. So don't worry about memorizing all this stuff. But I do want you to have a good understanding of how the system actually works, especially to understand how errors occur. They're orbiting the Earth around 20,000 kilometers, and they complete an orbit in approximately 12 hours. So one individual satellite will cross over any point on the Earth approximately twice per day. But these orbits are changing, right? So depending on where you are and what time of day, you might have a different satellite cluster you're working with that might affect how good your GPS data is. So these satellites broadcast on 2 frequencies, and these frequencies are compatible with different devices. More expensive survey-grade devices will have access to what is called the Precise Positioning Service, or PPS. And the standard is what your phone is actually talking to. It's kind of the default, less precise service. So I mentioned that Department of Defense used to have control over the precision. So in the past, it was possible for the Department of Defense to switch off, to turn on something called selective availability. So for certain regions of the Earth, say for example, the US wanted to have a military advantage in some region, they could turn off precise positioning for public users and limit it to just the Department of Defense authorized users. So now the standard positioning service at present, we're actually beyond the time period of selective availability. That's not going to happen again unless there's a major policy shift. The claimed standard positioning service precision is 7.8 meters, pretty similar to what we observed with your data, right? 95% of the time. And vertical accuracy of about 15 meters, 95% of the time. So notice that your vertical precision is worse than your horizontal precision. And after you finish this lecture, I hope you can understand why. It has to do with the geometry of where the satellites are relative to your position. That's why if you have like a Garmin GPS watch that you turn on when you're hiking or skiing or whatever, it still has a pressure-based altimeter because those are actually more precise than a GPS measurement of your altitude. All right, so to get a good signal, you have to have a direct line to a GPS receiver, meaning you don't want to have any obstructions. If we did the same experiment with your precision of your GPS devices in this room, I would expect it to look a lot worse because the radio signals are coming through the ceiling of Romney Hall, right? You have to remember, you're getting the satellite signal from space. It bounces off things. It can be blocked by buildings, right? If you have Sirius XM in your car and you've been driving downtown, like at least in my car, there's a couple of dead spots right on Main Street where some of the taller buildings on Main Street are blocking the view of the southern sky, so you don't get that good satellite signal. Same thing for GPS. You need to have a clear view of the sky. So the ideal situation is like clear skies, flat landscape on an open field, and when you're in mountainous terrain, it's a little bit more challenging. You might notice this if you're a person who occasionally tracks your activities, if you're hiking, running, skiing, walking, whatever. This is a screen grab from Strava. You can kind of keep track of the precision, right? And our assumption here is that the satellite imagery is really high precision. It's coming from the Landsat satellites. It's been overlaid on the landscape in a very accurate way. So where we can see things like Sourdough Canyon Trail, that's probably the true location. You can see my GPS track is like a few meters off the trail in this location. But here, it's right on the trail, and it's pretty good. You can kind of observe that drift when you look at your GPS data. In this case, based on the shadows of this left side satellite image, it really does look like that was a steep slope. It's possible that was blocking my direct view to the satellites. All right, so how do we actually measure these distances to satellites? Radio waves travel at the speed of light. We know that number, it's a constant. So it's essentially, it's about 186,000 miles per second. That is our rate. And so if we know when the signal was emitted from the satellite, and then your device also has a clock and can measure when that signal was received by your device, we have our time offset. So that's our t in distance equals rate times time. And then we can solve for that distance. This is assuming a straight line path, right? So any sort of deflection of that signal, change in its direction, for instance, if it interferes with the atmosphere, like if we have ionic charges in the outer atmosphere, that can interfere with the path of the radio signal and cause it to give us a false distance. We have to correct for it. So we have to actually use at least 4 satellites. That's a number I might ask you, by the way. And you can figure out why that is the case with these sort of graphical illustrations. So when you're figuring out distance from a satellite, you don't know direction, right? That radio wave is emitted in all directions. You could pick it up in any direction from the satellite. You could be in space. Obviously, it's likely that you are near the Earth's surface, but your GPS device doesn't actually automatically take that into account. So if you just had one satellite, you could be anywhere around the outer edges of that sphere, and the radius of that sphere would be your distance you calculated by measuring the time offset of the signals from the GPS. If we add 2 satellites into the picture, you're a little closer to satellite 2. Your possible locations are where those 2 spheres are actually intersecting. So in this case, you could be anywhere along this circle defined by the intersection of those 2 spheres. If we add a 3rd satellite, we can narrow that down to 2 unique points. However, it's not a unique single point, right? We still have 2 possibilities. One is out in space, one is on the Earth's surface. If we add a 4th satellite, that gets us to a unique location. We need to have at least 4 satellites in touch with our device to get a meaningful location. So how do we actually know that time difference? The GPS satellites are emitting sort of a random pattern that is known to GPS devices. Basically binary, right? Like 10, 10, 10 for certain periods of time. And your device can match up these changes in the signal. And that can be used to measure that time difference. However much time the signal is offset tells us how long it took for that radio wave to travel from space to your phone or your GPS receiver. The signal actually repeats every millisecond, right? So we're trying to get as much temporal accuracy as possible. So let's illustrate this timing offset. The precision of our clock does affect how accurate our locations can be. Because the radio waves are moving at the speed of light, obviously even tiny time errors on your clock on your GPS device will have a huge impact in how far that radio wave could have traveled. With a GPS-enabled phone, like a smartphone, we're getting automatic updates to our clocks from cell phone towers. We're actually getting them directly from satellites as well. So our clocks are constantly resetting themselves based on signals from much more accurate clocks. And that's how we can ensure that we have an accurate time on our device. So let's say we had, if we're measuring time offsets that are a little bit wrong, what that creates is a zone of error. So we could actually be located anywhere within this sort of polygon shape here based on the precision we are measuring those time offsets. Sort of like an error ellipse, right? That zone is our possible locations, and the size of that zone is going to be how precise our measurement can actually be. In the case of 3 satellites, all with time errors, right? We create a much larger zone of your possible locations. True location would be right here in the center, right? But the possible locations based on the ranges in time measured by the device is much larger. This is what gives us our errors in our GPS measurements. So there are a few different sources of error. I already kind of mentioned atmospheric effects. This can change the path the radio waves take, making the paths longer than a direct line. Kind of close related is multipath. That's when things are reflecting off of different objects, taking multiple different straight line pathways, making the path longer than it should be. The geometry of the satellite constellation, measurement noise, essentially like not being able to get a good signal or having a bad clock reading on your device, and some other sources as well. So atmospheric effects, this can actually bend the path of the radio waves. And in general, we understand pretty well how this works. There's actually planes flying around and stationary observation points on the ground that are measuring the electrical activity in the atmosphere that has the potential to interact with these GPS signals. And that is being broadcast to the satellites so that the signals can be corrected for that interference. So we know how this behavior works for the most part, so we can correct the majority of the errors that relate to atmospheric interference. But occasionally it's worse than other times, right? You might have like incoming solar wind. Have you heard of solar wind? It's like ions emitted from the sun. We get a lot of interaction with that in our atmosphere. It can really cause some issues with reading those GPS signals. Multipath is if the signal actually bounces off of a building, or in this case, the pyramids of Egypt, right? That would create a longer path that is received by your device as compared to just a straight line. That would give you a false distance that you're a little bit further from the satellite than you actually are. This one's kind of important to understand. It's abbreviated PDOP, and it's called positional dilution of precision. And if we break that down, it just means that certain orientations or geometries of the satellite arrays are better for locating yourself than others. On the left side of the screen, you can see 4 satellites that are kind of spread across the sky. That's the ideal scenario. You want to have satellites broadcasting signals from all different angles, directly overhead, on the horizon, etc. In the case where all the satellites are kind of in the same region, you're going to end up with worse GPS data. You might have seen on some GPS devices, you can actually generate a plot of where the satellites are, and you can see if they're all clustering together or if they're further apart. You can't see that on Google Maps, but if you download an app to your phone, like any of these GPS smartphone apps, most of them will have a view that shows you actually the geometry of the satellite cluster. So let me illustrate why that is the case. So if the satellites are further away, right, and all of these different sources of error are giving us a range of possibilities that are between these two circles, right? The radius could be as short as the inner circle or as long as the outer circle for 2 different satellites. If they are further away from each other in the sky, it creates this possible location kind of diamond zone here that has this shape. So watch what happens when they move a little bit closer together. So in the case where we have the same difference in the radius for the 2 satellites, if they are closer together, that permissible zone for your location is much larger by comparison. Just compare that again, right? Smaller diamond here, larger diamond shape here. So in general, you're going to get a better reading if the satellites are further apart from each other in the sky. And I want to also explain, this sort of geometrical reason is why our vertical measurements are not as good. And it's because when we are receiving a signal on the Earth's surface here, we're talking to one satellite directly overhead and like 3 or more that are more on a horizontal plane. Where those radii overlap, it's given us pretty good horizontal accuracy. But because of the way those circles or those spheres around the satellites that are lower on the horizon actually intersect with each other, it creates a really long sort of up and down error zone, like a permissible zone of your location. So this geometry is what creates the poor vertical precision. In the case where all the satellites were directly overhead, that would actually create really good vertical accuracy, but pretty poor horizontal accuracy. So because of the way the satellite orbits are designed, they are favoring the horizontal accuracy over the vertical accuracy. And that's because usually we can actually correct our vertical elevation, that is assuming we're on the ground. If you have a map of elevations, like a digital elevation model, you can use that to replace your measured vertical value with one that is known from the elevation of the Earth's surface. Any questions? I'm throwing a lot at you today. Does this make sense? Why vertical measurements can be bad? I think that is yes. All right, so how accurate are GPS devices? It depends on the type of device you are using. And we can have, if we had a cost specified here, right? The cheapest devices, the least expensive ones would be at the top. The most expensive would be at the bottom. So recreational / mapping grade, if you go to REI and buy a GPS device from Garmin or whatever other company, or just your phone, we can expect 7.8 meters 95% of the time using that, that CA code transmission. Autonomous meaning it means you don't have to actually do any work to correct the data, or you don't have to talk to any other sources of data other than the satellites themselves. A higher end recreational grade GPS might be able to get you a little bit better measurements, or what would be described as mapping grade, like for instance, a Bad Elf GPS mapping grade, like $250, $300 online. This will have something called differential correction, which actually gets some correction data from the ground control, broadcast through different radio signals all across the Earth. And that can get you better precision up to 5 meters. Sub-meter mapping grade, 10 centimeters to 1 meter, and then survey grade, you know, you'll have to have really high precision survey equipment to do this. You can get as accurate as 1 centimeter. So I find that pretty amazing. We just talked about all these different sources of error, but this system can actually get us down to 1 centimeter accuracy if you can get the right equipment and the right conditions. So for civil engineering, of course, this is like what you want, right? You want your structures you're working on to be in the right place. Okay, so if you haven't done this collection activity yet, you can still do it. Go to that manhole cover, and that's all I've got for you today. So have a great time in lab.
Two questions.
Yeah, sure.
Okay. So,